Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. It's my great pleasure to welcome back Richard Hartley, who's visiting us for a few days. He'll be here until next Wednesday. Richard is very well known in the computer vision field. He was one of the pioneers in projective structure from motion and multi-view reconstruction. And he and Andrew Zisserman wrote the very well-known book on that topic in the year 2000. Richard's also been a collaborator here with us. He's come visit us several times. He worked with us on some of the early work we did on 360-degree video walkthroughs. And today he's going to present us something he was just talking about at the CVPR Vision Conference, namely optimization techniques on manifolds.
Okay, thanks. So obviously, we're a small group here, so interrupt as much as you want to ask me questions on this as we go along. Okay, I'm talking about convex optimization on manifolds, but also particularly something to do with structure from motion here, applied to structure from motion. Now, convex optimization has been very popular fairly recently, since really the book of Boyd and Vanderberg came out, and there's been increasing interest in this subject. Reason is, in fact, that there are now efficient algorithms for doing convex optimization in lots of cases, and there's a unique minimum, and you know how to get to the minimum, and all these sort of nice things. The only trouble is, of course, most problems, particularly structure from motion problems, we come across are not convex problems, and so the question is to find out those ones that are, and so you can take advantage of it. Now, I'm going to talk in general a little about convex optimization as applied to manifolds and what differences you have to do when you're working on manifolds. And then I'm going to talk specifically about a structure and motion problem where I'm going to be talking about rotation averaging. So we're doing work on the specific manifold of all three-dimensional rotations, which is known as SO3. Three-dimensional manifold. So just some introductory material about convex optimization. Then to be able to really define convex sets, convex functions need to have the idea of what a convex set is, which is a fairly simple concept, which you're probably familiar with. You have a set, you take any 2 points in that set, and you take the line that joins those, then it lies in the set. So this set is convex, and this one is not, because that line goes outside the set. One of the nice properties is the intersection of convex sets is convex. And then there's a convex function, which really means that if you have the graph of the function and you join 2 points on it, then that line lies above the graph. So specifically, there's the formula which expresses it, but it's most easily thought of just in terms of that graphical concept. So it goes down, and you've got a nice minimum you can find by, in a sense, going downhill. So that's the convex optimization problem. The generic problem is minimize some convex function over a convex set. So sort of this sort of thing. Here's a function, and you find the minimum. And the properties are, in fact, has a single minimum on a convex domain. Well, that's not quite true. It can have a set of minimum all with the same value, where it's sort of flat on the bottom. But then it will be, the minimum will be attained on a convex set itself. So if it's, as I said, if it's flat on the bottom, then there are several minima. Sum of convex functions is convex. So if you're trying to optimize some function, each of whose components, which is the sum of several terms, and each term is convex, then the whole thing is convex, and so you're in good shape. Linear functions are, of course, convex as well. So you add linear functions to other convex functions. What you have is a convex function. Now, from elementary calculus, we know these sort of things. If you take the derivative of a function, then you have a stationary point of the function where the derivative is 0. And if the second derivative is less than 0, it's a maximum. A minimum when it's greater than 0, and If it's equal to 0, then you might have a saddle or you might have something or other else. But here's the case where we're interested in, really, where the second derivative is greater than or equal to 0. Second derivative positive, then you've got a convex function and the minimum. So that's nice for functions of a single variable, and functions of several variables sort of goes like this, that you have function from Rn to R. It has a stationary point when the Jacobian is 0, so potentially a minimum. And then, so there, for instance, derivative is 0. And then you determine whether that's a maximum or a minimum or whatever it is in terms of the hessian of the function. Okay? So the hessian is where you take all the second derivatives of the function with respect to x1, x2, or xi, xj. So that's the hessian. Okay? Now, if you look at the hessian, you can tell, in fact, whether the function is convex, concave, whatever. Diagonalize it, for instance, by an orthogonal change of coordinates, and the diagonals will be the eigenvalues. So then if the eigenvalues are positive, then it's convex. Okay? So it's like if the derivative is convex, it is positive, you have a convex function. Similarly, in general, if it's positive definite matrix, positive eigenvalues, it's convex. And if it's negative, it's concave. And if they're mixed, you have a saddle. So it sort of looks like this in the case where the function has all positive eigenvalues. You have this nice sort of shape like this. Here's all negative eigenvalues, and here's mixed positive and negative eigenvalues, and you have saddles. So, now, what about manifolds? So for manifolds, you've got to sort of define these same sort of ideas. What's meant by a convex set on a manifold? Well, first of all, what's a manifold? And I actually haven't got a slide for that. You should think of a manifold as being, in a sense, a surface. Right? So think of it as being a surface without any singularities, embedded in some Rn, in some Euclidean space. Okay? So, and we'll see pictures of them. So locally, it's just sort of flat and linear and smooth and everything. It's similar to some Euclidean space locally. Now, so what are geodesics? We use the concept of geodesics instead of line segments when we're talking about manifolds. So, and I'll show what geodesic is in a bit. So points in the set are joined by geodesics. So generally, therefore, you talk about on manifolds, a set is convex if points in that are joined by geodesics and those geodesics lie in the set. So that gets a little bit more technical than that, as we'll see. And functions are convex if they're convex functions on the geodesics, as we'll see. And so a function on a manifold is convex if the hessian is positive definite, and we'll say what it means by the hessian of a function defined on a manifold in a bit. And there's additional complexity because geodesics are not unique on this. So it gets a little bit more complicated. Some things carry over from Rn and some things don't. So the first thing then is, what is a geodesic? So a geodesic, just a big word for a fairly easy concept, which you're familiar with, I would guess. So you think of it in terms of curve. What is a curve on a manifold? So a path on a manifold, right, is just a mapping from some interval of the real line into the manifold. So just draw a path on the sphere, for instance, on the surface of the Earth. Path on the surface of the Earth is an example of a curve. And a geodesic is a particular curve which has these properties. It's sort of locally distance minimizing. Locally distance minimizing. We'll see in a moment. Let me just, in fact, go to the next pop-up here. So here's an example of a geodesic on a sphere. Right? It happens to be a great circle, what the geodesics here are. They're locally distance minimizing, which means although this curve, which goes around the backside of the sphere, is not the shortest path from here to here, nevertheless, I can break this up into little bits. Right? For instance, think of the dots here. This is definitely the shortest path from here to here, and this is the shortest path from here to here. So it's made up of shortest paths. Right? In fact, you can divide it up into intervals so that for any 2 points in that interval, it's the shortest path. Okay, so it's a locally distance minimizing curve. You can also think of it in terms of a thing moving at constant velocity on the surface, and then if the acceleration is always normal to the surface, then that's a geodesic. So for instance, of course, if you drive a car around the Earth, your velocity, your acceleration is radial, so perpendicular to the surface. Or you can think of it in terms of a taut piece of elastic band on the surface. So if you take an elastic band and here and let it pull, it will settle on some curve, and that will be a geodesic. In this particular case here, if you look at that curve, if that were made of rubber, right, it's still an equilibrium point for that curve. It's not stable equilibrium. I mean, this can be continually deformed into a shorter curve, but it is in stable equilibrium if you think of a force on a curve there. So
the curve rose in length for a while before you flip it over, right?
Well, not in this case, it doesn't.
I see. It's always...
No. It's sort of sitting on an unstable equilibrium. If you move it slightly off, it'll sort of shrink. One which goes as shorter than a complete half turn, then it will certainly be in stable equilibrium. And if it goes from the pole to the pole, it'll be in sort of neither stable nor it'll be stable equilibrium. Okay, so here are some examples. Geodesics can be quite complicated. So here's on a torus. These are all geodesic curves. This is a so-called pretzel. And curves, they go round and round and round and round. This one, in fact, happens to be closed, which is unusual. Geodesics are not generally closed. In other words, they don't come back to the same point in general. On a cone, here's an interesting case where, in fact, here let's take 2 points. There are at least 3 geodesics which join those 2 points, right? 1, 2, and round the other side. In fact, this surface has the interesting property that it's flat in the sense that the so-called Gaussian curvature of that surface is 0, which means that I can sort of cut the cone and wrap it out onto a flat surface, right? A sphere, you cannot do that. You cannot cut it and flatten it. Likewise, this you can't. But that means you can actually generate the geodesics on a cone by drawing a straight line with maybe in paint on the surface and rolling the cone, and the paint will transfer to the cone on a geodesic, similarly with a cylinder. So these are examples, all examples of geodesics. This is, as I said, an important one to bear in mind that geodesics between 2 points are not unique, right? And there's the difference between what you have in Rn, where points between lines in Rn are unique. There's only one line. But here there are several, in a sense. Geodesics, and sometimes they can even be of equal length. And on a sphere, the geodesics are the great circles. Okay? So intersections of a plane through the origin. So the next concept which is important here, this is a little bit of a tutorial on Riemannian geometry here that I'm giving, is the exponential map. Right? Now, I was always confused when people talk about the exponential map, thinking, what has this actually got to do with exponentials? Well, in a way, not so much. All it is, it's a fancy word for the following concept. You take a manifold, the dark grey thing, and take a tangent plane. I don't think these are surfaces. Take the tangent plane, and you take a vector in the tangent plane. And you wrap that vector, you start out with a geodesic heading in that direction and go for the length of the vector. In other words, you sort of take that and wrap it around the manifold. And that gives you a mapping from the tangent, from that vector which lies in the tangent space, to a point on the manifold. So the exponential map is simply a mapping from the tangent space at a point to the manifold itself. Right? And there's a thing called the logarithmic map, which does the opposite. You take a point here, and it goes back to the vector which, would get you there. So if you go back to the cone, for instance, you can see that if I head out in this direction, there's a little space around here a little patch around here that I can go and map by the exponential map down onto the sphere. But the logarithm map is not unique. Just as the logarithm map in the complex plane is not, for complex numbers is not unique, neither it is on a manifold. There are several directions I can get to get from here to here. I can go out along here and get to there, I go out along here and get to there, or straight across. And so each of those vectors are the logarithm of that with respect to the tangent space here. So it's not unique. Okay. Finally, gradient and Hessian. Remember, I defined convex functions in terms of gradients and Hessians, in terms of Hessians, with the Hessian as positive definite. If the gradient is 0, you potentially have a maximum of a function. If the Hessian is positive definite, then it is a maximum. So let's just think how this works on manifolds. So suppose you have a manifold M, and you've got a function from the manifold to the real numbers. Okay? Now, and you suppose you have the exponential map at a given point. So at x, this is the exponential map at this point x. And now if you take the function from the tangent space through the manifold and compose it with the function f that you're interested in, then I have a function now from Rn to R, and I can find gradient and Hessian in the usual way. Hessian, remember, is defined in terms of functions from Rn to R. And if I have f, I can create such a function. And then you have that the gradient defines a vector in the tangent space, and the Hessian is in fact can be represented as usual by a symmetric matrix, and if that Hessian is positive definite, then the function is convex. So convex function of the manifold, a function is convex at a point x if and only if the Hessian is positive definite at x. Okay? What it also means, the other alternative definition for a convex function is just the same thing as it is for same thing as it was for sets in Rn. If you have a function defined in an area around here, and you take a geodesic, then that defines a function on that path along that geodesic. And if that function confined to that geodesic is convex, then the function is convex. So there are equivalent definitions as one can prove. Okay, that's sort of general ideas about convex functions in Rn. We're going to look now at rotation space, because I'm particularly interested in applying this. In fact, two rotation spaces. In fact, I've set this as a sort of an area that I want to look at a bit. This idea of functions in convex functions on manifolds, and the simplest sort of one that at least non-trivial one that you might look at, is rotation space, and it's interesting in our area. And I don't have much in results on anything other than rotation space. Some of the results obviously do extend, and others maybe don't. So let's just look at rotation space as an example. So I think we all understand rotations, right? Rotations. Well, there are things about rotations that perhaps not everyone here is familiar with, but let's just go through some of these things. One of the most important representations of rotations is as quaternions. Okay, we all know, I suppose, that rotations can be represented by 3x3 matrices. I'm thinking of three-dimensional rotations, right? So they're represented by a 3x3 orthogonal matrix. But another very important one is the quaternion representation. Quaternion is a 4-vector, and a rotation is represented by a unit quaternion. And what it means is, if you write the vector as q as cos theta on 2 and sine theta on 2 times v, where v is a 3-vector. In other words, you take the last 3 and consider it as a vector, and that one, q0, is cos theta on 2, so that tells you the angle of rotation, and the vector v tells you the axis. So if that's the axis and rotation through the angle theta, that is the rotation represented by that quaternion. Okay? Now, one of the things here is that both q and minus q represent the same rotation. Okay? So that's because, for instance, a rotation about some angle about this axis is the same thing as a rotation through the negative angle about the oppositely directed axis. So both q and minus q represent the same rotation. These quaternions, there's a quote that I've found in a book which says that if you've spent all your life studying rotations and then you'd only then discovered quaternions, you would think that your life had been wasted. So But maybe a lot of computer vision people wasted their lives thinking of rotations. I don't know, because it was really Berthold Horn who really introduced quaternions into our field of computer vision. Probably quite a while ago now, maybe 20 years or more. I can't remember the date of those papers, but yes. And now, one of the interesting things about this representation is that if you have a quaternion and the rotation matrix that represents which represents the same rotation, there's a thing called quaternion multiplication, which I haven't defined. But if you multiply two quaternions, that gives you the same rotation as multiplying the matrices. So this is an algebraic isomorphism, you might call it. But so in other ways, you can use quaternions actually to multiply matrices and to work with matrices. In fact, quite efficiently. It's more efficient, in fact, than multiplying matrices together in terms of operations. But one of the other things about it is that it's not only algebraically like that, isometrically, quaternions are like rotations as well, in that, okay, I'm going a bit ahead here, but if you ask yourself how close are two rotations to each other, I have two rotations, how close is one to the other? Well, what you'll normally do is take, if they're R1 and R2, you take R1 times R2 minus 1, that is a rotation from one, think of them as coordinate frames, a rotation being the orientation of coordinate frames. So I've got one coordinate frame and another one. How do I get from one to the other? Well, I rotate, and by what angle do I rotate? Tells you about how far these are away from each other. So that's the angle between two rotations. And that is exactly the same thing as the distance between two quaternions. If you think of the quaternions, as I said, as unit quaternions, so they're points on a sphere, in fact, a three-dimensional sphere lying in R4, and if you take the distance along that sphere from one vector to the other, that is the distance in the quaternion sphere, and that happens to be exactly the same as the angle. Well, there's a factor of 2 difference there, as a matter of fact. So you can think of all rotations which are close to another one form a ball on the sphere, or a circle on the sphere. There's actually just one little complexity there, in that I said that both one rotation and its negative represent the same rotation. So you really take the minimum distance from either there to there or there to the opposite is what the quaternion distance might be. Okay? So quaternion is a very useful representation of rotations. Another one is angle axis, where you, in a sense, almost forget about the first component of the quaternion, which doesn't actually give you so much. You've got all the information in the last three. Because you've got the vector v, which is a unit vector, and you've got the sine theta. But what the angle axis method is you sort of say, you take the vector v and multiply it by, take the unit vector and multiply it by the angle of the rotation, and you get the angle axis representation. And that is sort of like taking the sphere, the quaternion sphere, and flattening it out. Think of this thing as being a piece of rubber. You cut it in half at the equator because you don't need both the bottom and the top halves, and then flatten it out, and you get the angle axis rotation. This is a map of the Earth with what's known as the azimuthal equidistant projection, which gives you the same thing. So, in other words, you can think of this, if you want to represent a rotation, this is actually my favorite representation of rotations for any computational purposes, is through the angle axis method, where you represent a rotation by a vector, which is the axis, multiplied by the angle that you rotate through. And so all rotations may be represented by a ball of radius pi, because the maximum rotation you need is a rotation through pi. There have been a few papers recently on what's known as no, they haven't. It's equivalent, but I'll just introduce this one just for a moment. The Gnomonic Projection. I don't know if you know the word gnomon. It's a gnomon, or gnomon, or I'm not quite sure how to pronounce it. Gnomon, perhaps. Gnomon is, anyone know?
So big, right?
Not quite. This is a very obscure word. It's a little thing in the middle of a sundial which throws a shadow to tell you what time it is. That's the gnomon. And I'm not sure what it has to do with this exactly, but that's what the word comes from. And okay, so if you think of this as being the Quaternion sphere, so it's a three-dimensional sphere, and you take a plane tangent to the sphere, so this is actually not a two-dimensional plane, but a three-dimensional plane in R4, and you project from the center of the sphere, then that gives you a mapping from the Quaternion sphere to the plane. Okay? And it has the nice thing that opposite points on the Quaternion sphere map to the same point, which is good because opposite points are the same thing, and has the extra property that great circles here, which are, as I said, geodesics, map to straight lines in the plane. Okay? So we can, via the Gnomonic projection, we can take rotations to an R3 plane in R4, in other words, a three-dimensional plane, in which geodesics in rotation space are represented by straight lines in space. And furthermore, in any sort of reasonable sense, what you might call convex sets in rotation space are in fact convex sets in Rn, and we understand Rn, R3 in this particular case. It is it is related to what's known as the Cayley transform, which has come up in a few papers recently. People have sort of discovered the Cayley transform, which is a way of representing rotations. And what that is, if you take a rotation R, the Cayley transform is R plus I inverse times R minus I. So that gives you, the Cayley transform takes a rotation matrix and ends up with a skew-symmetric matrix. This is a skew-symmetric matrix. And alternatively, if this was skew-symmetric, you end up with a rotation. So it's a bijective mapping between rotations and skew-symmetric matrices. It's its own inverse. Gives a one-to-one map between rotations and skew-symmetric matrices, and people have used this for computation. Now, it is, in fact, as it turns out, related to the Gnomonic projection in that if you take, okay, now a skew-symmetric matrix of size 3 by 3 only has 3 elements which are non-zero. I mean, if this was skew-symmetric, the diagonal is 0, and you've got 1, 2, 3 elements, and these are the same, except with the opposite sign. So a skew-symmetric matrix has got 3 parameters. Now, if you go from a matrix to the Quaternion sphere, and then via the Gnomonic mapping, that's the same thing as going from R via the Cayley transform. So the Gnomonic mapping and the Cayley transform are effectively the same thing. We're not going to talk about the Cayley transform. The Gnomonic mapping, however, is very useful because it allows you to understand everything is, you're mapping into Rn and you're preserving geodesics become straight lines and convex sets become whatever. So, okay. What are convex sets in rotation space? So, there are 2 ideas here, weakly and strongly convex sets, which I'll define like this. Set is weakly convex if 2 points in a set are connected by a single geodesic lying in the set. Right? So 2 points are joined by a geodesic, but not 2 of them, because otherwise you get confused. And if that geodesic happens to be the shortest geodesic, then you call the set convex. Now, the things that happen here, if you have the Quaternion sphere, here's a set which you'd think of should be convex by all sorts of any intuitive idea. And there are 2 points. In fact, you can join them by a geodesic, a great circle, lying in the set. However, since this is a Quaternion sphere, well, yes, you can join them, but it's the same as what lies underneath as well. And that point, a point here is the same as a point here, remember, in Quaternion space. That point is really the same as this. In fact, the shortest line from that rotation to this is that line there, which does not lie in the set. So the shortest geodesic does not lie in the set. So I call that set weakly convex. There's the shortest geodesic. Weakly convex, but not strongly convex. It's only strongly convex if the shortest geodesic lies in there. One of the nasty things about weakly convex sets is that you can take 2 of them. Now, if you go via the Gnomonic projection, a convex set can be split into 2 bits, and you can get a situation where you can take 2 convex sets and their intersection can be 2 pieces, right? Unlike in Rn, intersection of 2 convex sets is convex. If you take weakly convex sets in rotation space, the intersection of them can be 2 parts. And so here's a sort of a rather full slide that says much the same thing. Sets weakly convex of 2 points and set are connected by a single geodesic. Convex, if that's the shortest geodesic, various properties. Convex sets are similar to convex sets in Rn. You can map via the Gnomonic projection, and there you've got the same thing. Convex sets cannot be too large. There's a limit on the size they can be. In fact, they must be contained in a ball of radius 2 pi on 3, it turns out. And weakly convex are more difficult. Yes?
So weakly convex sets can be disconnected?
No, a weakly convex set must be connected because 2 points have to be joined by a geodesic. But that geodesic may not be the shortest one. Right? And if you take 2 of them, here's the example, right? This is a weakly convex set. In the 2 points are joined by a single geodesic inside the set. But the shortest geodesic lies outside the set. That is not the shortest geodesic from there to there. This is.
So when you think of the Quaternion sphere, is it really the full sphere or the hemisphere?
Well, you can think of it in different ways. You can think of it as the hemisphere, or you think of it as the full sphere, but opposite points are actually the same. Yes.
Topology, like when we talk topology, say these 2 points are really the same.
Yes. Yes. In fact, so what you have is a sphere with opposite points identified. It's actually projective space.
Yeah.
In fact, so the rotation space is in fact topologically R3 projective space, P3, which we're familiar with through structure and motion. So in a different way.
So in this particular case, since top part is equivalent to the bottom part, you don't consider them to be disconnected.
No, you don't. They're the same point. It's really, they're the same thing. It's in a sense, it's a bit like thinking of rational numbers. 1 on 2 is the same as 3 on 1 on 2 is the same as 2 on 4 is the same as 3 on 6. They're just different ways of representing the same thing, and these are just 2 points which are the same, right? They're the same. Okay. Better just get along with it a little bit here. Distances between rotations. Okay. We need to talk about distances between rotations. In many ways, many people have talked about distance of rotations with different meanings. The usual meaning that I like is this angular metric, which is if you've got 2 rotations, 2 frames, how far do you have to rotate one to get to the other? That's the angle metric. And as I said, it's very much the same as the distance on the Quaternion sphere. But there's also the chordal metric, which is just take 2 rotations as matrices, subtract them and take the Frobenius norm, sum of squares of distances. That's also a norm for distance measurement for matrices. And it's, in a sense, it's the Euclidean distance in the natural embedding of rotations in R9.
Sorry, Richard,
yes?
Metric, you're talking about the shortest rotation that maps onto the other.
Yes. So it's a rotation through less than pi radians. Right, so no 2 rotations can be further than pi apart, right? And then there's a Quaternion metric, which is just the distance between these vectors as vectors not along the surface of the sphere, but directly cut across, the distance between these 2 things, right, between 2 4 vectors. And so it's actually the minimum of R minus S and R plus S, because you have to take account of the fact that 2 Quaternions represent the same rotation.
Then there's another one which is equivalent to the first one, which is the ratio of the 2 quaternions, right? When you divide one quaternion by the other, that gives you basically the angle. It gives you a quaternion.
Yes.
Whose magnitude is the angle.
Whose magnitude is
the R times S inverse is basically quaternion R divided by quaternion S, right? They're equivalent.
But R times S inverse is a unit quaternion, though, so its magnitude is still 1, so that's not really correct.
No, so, okay, it's not the magnitude, it's the part that is the cos, or the sine theta part of the quaternion, right?
Well, yes.
You pull that out, so it's the angle represented.
It's the angle.
It's the angle.
It
so
is, yes.
There's another way of writing down the angle metric, which involves quaternions as opposed to rotation matrices.
Indeed.
Yeah, I'm just saying that because that's often the way I implement it.
Yeah, you can compute it from the... yes, you can compute it.
You can compute it without explicitly forming the R matrices, and it might be more stable if you do it that way.
Indeed you can.
Yeah.
And the other one, the Quaternion metric, you can get by taking the inner product of the 2.
Right.
And that gives you the well, you can just do it like that. That's the cosine of the angle in any case. And so you, You can
Those
do
kinds
it.
of small angles are notoriously hard to.
True. Right, and they sort of look like this. If the angle is theta, then here's theta squared. But the chordal metric looks like this, and its square looks like this, and the Quaternion metric looks like this, and its square looks like this. The interesting thing about the chordal metric, neither it nor its square are convex on the whole set of rotations. Quaternion metrics, this is not convex, its square is. And for the angle metric, both the angle metric and its square are convex. So this is a good one to work with. Though, yeah. So, as I said, the angle metric is convex everywhere except on the plane at distance pi from S. Now, I'm going to get now to what I'm want to do is actually average rotations. So if I take the sum of distances, supposing I've got a bunch of rotations SI, and I take this distance metric, that distance can be any of the ones that I want to find the R that minimizes this. It's closest to all the SI in some sense, where this is some distance metric and P is some power, so that would be corresponding to a P norm, and usually P is 1 or 2 in what I'm interested in. It's convex on open balls of SI, around SI with pi, and on the intersection of these open balls, the functions are going to be convex for my angle metric. So these distance functions are nice and convex everywhere except on a set of planes, if you think of this, or the set of rotations which are a distance pi. In other words, if you think of these in terms of on the Quaternion sphere, let's draw the Quaternion sphere. This will do. If I take a point here and take the sphere, which is the hemisphere, the equator in a sense, which is a distance pi away from this, there's a discontinuity there of derivative. But if you've got a bunch of rotations and you draw those I call them planes, then the function is convex except on those. And on any convex set which doesn't contain those, it's convex. So we're in good shape. So let's have a look at rotation averaging problems. There are a couple of problems that I want to look at. There's this one where I want single rotation averaging. Given a set of rotations, find the rotation S that minimizes this function. In other words, it minimizes the distances to my Ri. Okay? And that's the cost of S, and I want to minimize the cost of S. Usually, as I said, P is 0, 1. Now, there's multiple rotation averaging. Yes?
What is P?
P is 0 or 1. Sorry, P is 1 or 2. It's equivalent to whether you're doing LP norm or L1 norm or L2 norm, right?
LP.
Yes. It's just a power. Just the power. It's squared, or it's just the distance itself. So distance of sum of squares of distances is just sum of distances, right? Multiple rotation averaging. So in multiple rotation averaging, what you have is you've got a bunch of relative rotations, Rij, and we'll see this, and you want to find the Ri and the Rj. P may be L1 or 2. So let's have a look at this. In the single rotation averaging problem, this is the standard structure and motion thing. You've got a moving camera which moves from here to here. From 5 corresponding points in 2 images, you can compute that motion, right? The so-called 5-point algorithm for computing relative orientation of 2 cameras. Very fast, about 35 microseconds in my implementation. David claims about 20 microseconds, which I believe he can probably do it in that time. So it's very quick. You can do this 30,000 times a second, so you can take samples of 5 things. And one way of estimating the rotation would be to take sets of 5 points, compute the rotations, and average them, right? Rather than using a ransack approach, just try averaging the rotations. Take many different sets of 5 points and average them. Individual estimates can be noisy. The rotation you get from 5 points, if the 5 points you use are bad, can be quite not very good. So you need a robust way of averaging those. So in the single rotation averaging problem, you have several estimates of rotation. What is the best way of reconciling them? From 5 points and 2 views. I said exactly the same thing again on that slide, really. Now here's the multiple rotation averaging problem. I move the camera through some path. I have several cameras, and I can compute so I can compute R12, which is the rotation from there to there. I can compute that rotation, and I can compute that rotation. But they must be related. You need, for consistency, that R13 has to be R23 times R12. Rotations form a group. And so what you want to do is actually find R1, R2, and R3 that come as close as possible to satisfying this relationship. Rij equals Rj times Ri to the minus 1. So you're trying to find the absolute rotations giving the relative ones. So let's have a look at where this may be applied. This is what I applied it to. The Notredame set, right? 569 images, 280,000 points. It happens to be 42,000 pairs of overlapping images, so which have more than 30 points in common, 42,000. So given that you can compute the relative orientation in 35 microseconds, you can easily handle 42,000 of these things. So what you want to do as a task is find the orientations of all the cameras. Right? And as I said, rotation averaging turns out to be a nice convex optimization problem on the rotation space. So the strategy is, for each pair of cameras, find the relative orientation Rij. And to do that, you take sets of 5 points and use to compute the relative, For each pair of cameras, find the relative orientation Rij, right? And that's done by averaging 5 points. Take sets of 5 points, and I average them, average the individual rotations to get Rij. And then average this multiple rotation, average the distant estimates to get the best average rotation. Yes, that's what I said. Then, the first one you'd
normally do with ransack, right? You wouldn't just randomly sample and average all of things. You'd count the outliers, right?
Well, yes, you can. I'm suggesting this is a possible way of doing it alternatively rather than do ransack. But really, since, in a sense, you need the rotation averaging in the second step, which is the multiple rotation. So I'm just, as an exercise, seeing how well it applies to the single rotation averaging as an alternative to ransack. You could use ransack in the first step alternatively, but in the second step, as you'll see, you need rotation averaging. So since the paper's about rotation averaging, I'm using the rotation averaging instead of ransack.
Okay.
Then I initialize the absolute orientation of all the cameras by propagating over a tree, as we'll see how. And then I do average rotation individually, assuming the neighbors are known. So that was a bit quick, but let's have a look at it. So each of these is supposed to represent a particular camera, and they're joined by an arrow if you can compute the rotation between them, right? And so you have this connected graph, and you've got the relative orientations between 2 points. So then I select any given point. Well, I actually select the one with the greatest fan out, and assume that the orientation of that is the identity. I mean, you can assume that is your reference frame, and then just by propagating out from there, since I know the relative orientation, I can compute. If I know that, and I know the relative orientation, I can know that, etc. By going over a tree, I can get an initial orientation for every rotation in the tree. Not necessarily very exact, but it's what it is. And the second step, then, it's a sort of a message passing algorithm, as Noah was talking about at CVPR, where in fact you now say, supposing I know all the other rotations, and what I'm going to do is I'm going to re-estimate this one, the blue one. Now, if all the rotations, these ones are known, and you know the relative orientations, that gives you an estimate, 4 different estimates in this case, of that rotation. So you average them, right? And then do that over and over through the whole thing and get the result. So the question is, how do you average rotations? It is a convex problem. That's where we started out. If p equals 2, it's a least squares averaging problem, and it's usually simpler, but it's not robust to outliers. I'm looking here at L1 averaging because it is robust. I've unfortunately gone a little bit slow at the beginning, so I'm going to have to speed up a bit here. There are various methods which have been proposed from L2 rotation averaging. There are exact solutions for that, in fact, which minimize not the angle metric, which minimize the caudal metric, as it turns out. You can minimize the caudal metric easily. You can minimize the Quaternion metric with a little bit more problem. The only difficulty with the Quaternion metric is the ambiguity between the two different representations. But for the caudal metric, there are two different algorithms I know of which will do that.
But the Quaternion one is, in practice, trivial, because you always basically flip each vector that is too far away from the current estimate, right?
Yes. Well,
I mean,
yeah. If they're close together.
They're close together.
Yes, there's no problem.
Otherwise.
There's no problem. If they're not close together, it's sort of NP-hard type of way of doing it. Whereas the caudal metric, it's closed form.
Closed form solution, but not particularly good. Well, anyway, you'll tell us results.
It makes very little difference, actually.
Does it? Okay.
Very little difference, yeah. It's very little difference. But L1 averaging is what I'm interested in.
So the main motivation is robustness, right? Robustness
Yes.
is really
the motivation for doing L1 is robustness.
Yeah.
Right. Well, the difference between, so just to get back, I'm not going to show why the caudal metric is, but the real difference is the caudal metric is very closely related to the angle metric. It's just it's sine of theta on 4, and for theta small, it's sine and theta itself are the same thing, right? So, but L1 rotation, L1 averaging is an interesting problem with long history, even in Rn, okay? In Rn, so say in R1, the L2 averages several points the mean. We just take a bunch of points, real numbers, take their mean, that's the L2 average. The L1 average turns out to be the median. And we know that the median is more robust to outliers. You've got a thing which is way off, doesn't make a lot of difference how far it is away, it's just... but and you can, there's in fact a linear time algorithm for finding the median, right? But in R2, the problem is a classical problem, goes back, it's known as the Fermat problem, sometimes the Fermat-Torricelli problem, 1636, also sometimes the Weber problem, Fermat-Weber problem, there's so many names, and then there's a bunch of recent work, eventually, so Fermat-Torricelli solved for 3 points in the plane, right, very simple. Weber gave an algorithm in 1906, which had to do, it sort of worked like this. You've got a bunch of points in the plane, and you want to find the point which minimizes the distance, sum of distances to all these points. And what he was interested in is you may have iron ore, coal, water, or something. Where do you put your factory to minimize the distances? So this is a problem that's important in that sort of context. So what his solution was supposing you take a table, and you mark all the points on it. Now you take an electric drill, maybe in 1906 took an ordinary drill, and you drill a hole through the table at each point, and you hang a weight on a string, and you connect all those strings together at one point, and where it comes to an equilibrium is the point you're looking for. So he had this solution for this. So not practical I suppose, for us these days, but nevertheless a solution. Weiszfeld in 1933 came up with a problem. This is a paper written by Weiszfeld, a Hungarian mathematician. He wrote it in French and published it in a Japanese mathematical journal. And it gives a nice closed form an iterative approach for doing this, which I'll discuss. More recent works is doing some stuff on manifolds, including Riemannian manifolds in 2009, 2010, which in fact we discovered after we'd done this work and saw that we'd been in a sense preempted in this, but nevertheless it's the way it is. So for 3 points, the Fermat point is the point, in fact, minimizes distance. Those is the point where those reach 120 degrees. It means that if you have unit vectors going from there, in each of those directions they're in equilibrium, and that's really why it works like that. Now, it turns out in Rn, this is a gradient descent problem. The cost function is distance from xi to y. Xi is given, you have to find y, find the distances, which is that. It's convex, has a single minimum, unless all the xi are collinear. The gradient happens to be the sum of the unit vectors. Take all the vectors and divide by their length. And so you can think of a gradient descent algorithm where you take yt as your current estimate, you take that current estimate plus some step size times the gradient. Okay? Here's the gradient direction, and that gives you the next one. So if you're working in L2 distance, your gradient is the sum of the vectors. In L1 distance, the sum of the unit vectors in all directions. The only question here is how to find gamma t. What is the step size, right? And normally, gradient descent algorithm is a bit of a pain in the neck because if you're doing gradient, you have to search along the gradient direction for the right step, and that means evaluating the function many times. But so what Weiszfeld did, he came up with a closed form formula for the step size. Very simple. You put the step size gamma t as 1 on the lengths, sum of 1 on the lengths and 1 on that, right? And that is your step size. And it turns so the update step now has this very simple form where you take the vectors from xi to the current estimate, divide by the length, and then divide by this as the step size, and that gives you the next. So very simple, very fast. Now how do you, and provably convergent. That's the point. Proved convergence in 1933. Now if you do it on a manifold, all you have to do is start at some point, and you've got a whole bunch of points on the manifold. You map them to the tangent space, do a step of the Weiszfeld algorithm in tangent space, takes you to a new point, map back to the map where you are, back to the manifold, and then take the new tangent space at that point. So we're in a sense reparametrizing at each step. Just iteratively, all you need to do this is have two maps. The map, which is a logarithm map, which goes from the manifold to the tangent space, and the exponential map, which takes you back to the manifold. And with those two things, you can apply the Weiszfeld algorithm. And it's, in recent work, can be proved to be convergent on an arbitrary manifold as long as it's a manifold of positive curvature. So that's basically saying that. So I'll just get finally to the results. But, all right, so the steps, you find initial estimate at any time, apply logarithmic map to get to map to the tangent space, apply a Weiszfeld step in the tangent space, and then go back to the new point in the manifold and form the tangent space there and keep going. Okay. Results on rotation averaging. This is the result of L2 rotation averaging. This is L1. Converges a lot faster. It converges to a much better solution with respect to ground truth. Right?
Ground truth here being whatever Noah's bundler produced?
Yes. That was my best ground truth that I had. So let's have a look how this works. Timing and accuracy on the multiple rotation averaging problem of the Notredame set. So here is the method which I use for computing the individual Rij, the 5-point algorithm. And the 20 means that I've done it 20 sets of 5 points. And 10 means that in the multiple rotation averaging problem, I am, in the multiple rotation averaging problem, I'm going through and re-estimating each rotation 10 times. Okay? E-bundled means I'm actually using complete bundle, the best algorithm I can think of, really, for computing the individual Rijs.
And your 5-point averager to get the pairs is an L1, right?
Yes.
So it's getting the robustness, some of the robustness that a ransack would produce.
Yes.
Okay.
Everything's L1.
Yeah.
If you do e-bundle, so you get these Rijs by bundling rotations, it takes a lot longer. There's a Sampson distance, which takes significantly longer as well. And the results, and this takes 36 seconds for the final rotation averaging. This is the time it takes to compute each of the Rijs. This is the time it takes to compute the absolute rotations by the multiple rotation averaging, 36 seconds. This is doing 168 seconds to 42,000 Rijs, okay? 36 seconds to then do the Weiszfeld averaging.
Was Weiszfeld averaging applied to all points in parallel and then done in several epochs, right? Keep going around.
Keep going around 10 times.
Oh, 10 times, yes.
Yes.
So that basically, that row is the corresponding breakout of the previous row, the component of that, which was the 10.
Yes, it doesn't actually probably make sense, does it? It apply to the...
That's fine. I mean, you
Yes.
wrote the parameters down in the left column. You said
Yes.
20 rounds for each Rij, and then 10 rounds for the global, for the
Yes.
multiple.
Yes.
And then you produce the sum number there and the breakdown. Okay.
I have, incidentally, a slightly more complete graph in the paper, which has got slightly different parameters there and showing the difference. L2 averaging takes 10 seconds into 36, so the L1 is almost as fast as the L2 averaging here. Right, well,
It's a single
almost.
step convergence, right?
Yes. Yeah. And the accuracy, I'm getting 0.93 degrees. So I'm getting an error of 0.93 degrees with respect to ground truth from these, which I think is pretty accurate. L2 clearly doesn't do as well, though it's in some sense even maybe surprising that it does as well as it does, given that sometimes your RIJs. But you've got two steps of robustness here. First of all, you've got the averaging to get your RIJs accurate, and then you've got the averaging of in the graph, where you've got many estimates. Average fan out is 80 in this graph. So you're averaging 80 things, and if 20 or 30 of those are bad, then it doesn't really matter because you're doing this L1 averaging, so you can get quite accurate, less than 1 degree. Okay? This sort of just shows the graph of L1 against L2, L1 against L2. Yes?
You said average fan out is 80, means that's degree, right?
Average fan out in the graph, each thing is connected on the average to 80 other cameras directly.
Okay, so that's degree,
Yes.
right? Degree of that node.
Degree of that node, yes. Yes. It's quite highly connected. Okay. I'm not going to go into this. I'm going to stop at this point. But I have started working this out on the essential manifold. And the only problem here is that you have to compute what the geodesics are on the essential manifold, which is quite a significantly different problem. They have quite a complex form like this as the product of 3 rotations, in fact. And to get that, you have to solve this set of 5 simultaneous differential equations to work out. There's probably a better way. In fact, my coworker says he's got a better way, but I
don't know if there's a better way. It just seems like something that's going to take you a while.
That took me a while.
Well,
You start with this and you say, this is hopeless, and then you start noticing things about it, and then you eventually get it.
But
Yeah.
even so, you've got a PDE solver inside your inner loop, right? Each time you do a projection.
Oh, no, because having solved them, you get a closed form for what the geodesic is. This is the geodesic closed form.
So you have an analytic.
You have an very simple
You're
analytic
saying that's
solution.
the solution
That
to
is
the
the
equation.
solution to that differential equation
Okay.
problem. Yeah, so that's simple. That's very simple, actually, and that's basically it.
So just for the rest of the audience that may not work on structure for motion as much, what does it mean to be doing essential matrix averaging? How will that be used?
Okay, so that means that I'm taking, once again, a 5-point algorithm, and I'm getting not only rotation, I'm getting rotation and translation, right? So I want to estimate, I've got several estimates of rotation and translation. I want to get the best estimate of rotation and translation. In this work that I've described so far, I'm throwing away the translation, not worrying about the translation at
And this
all.
will be useful for deriving robustified pairwise estimates. You haven't started, or maybe it's not possible to do this in a multiple essential matrix formulation.
The only problem there is that you don't know the scale of the rotation.
Right.
Yes. Yeah. Yes?
I was curious, did you include the SE3 problem? If you have the scales, then is the parameterization for the geodesics as easy as SO3?
Yeah, well, I prefer actually to work in the essential matrix manifold because you don't know the scale, and also because in that particular case you have these nice things which are bi-invariant metrics, SE3 being a non-compact manifold because of the E part. There's no left invariant, it's not invariant with respect to change of basis point in the sense, and so. But yeah, sure you can. If you want to separate the translations from the rotations and average in that way, yes, you can do it. You can do it that way.
You can get the scale from triplets, right?
Yes, you can get the scale from triplets. In fact, well, I mean, in earlier work with Christie Sim, for instance, we basically did that, except we were using SOCP to find the final version of this whole thing, and that, we're using SOCP to complete the the translation, having got the rotations, that's a very slow way of doing it. Closed form in a sense, but I mean, there's a unique solution. It's minimizing L infinity norm, but it can be done. So, but there are lots of ways of getting translation once you've got rotation. Right, Carsten Rother, we did some earlier work and various things, linear ways of doing it. Yeah, so.
Good.
Okay.
Are there any other questions from the audience? Okay, thank you very much.